Okay, in this video I'm going to be talking about how the changing of a concentration for a system that's already at equilibrium will change where the equilibrium for that system exists. So here's our system, some gas A plus some gas B is forming the new compound gas AB. So we can imagine that since we're supposed to be at equilibrium, we have a bunch of A's and a bunch of B's floating around, and we have some AB's floating around as well. Maybe just for the sake of argument, I'll make more AB's. And we're at equilibrium, which means these reactions haven't stopped, but what we've figured out is that A's and B's are splitting up as fast as A's and B's are coming together. And so for every one of these that's created or destroyed, another one is created, and that's what we mean by being at equilibrium. Okay, now I want to imagine the change where I draw or where I add a whole bunch of, let's say, AB to this mix. So now I'm going to add an AB here, an AB here, and an AB here. So those are my new species in my equilibrium. Where there used to be, I'll add one more just to make the math a little easier. Where I used to have 4 ABs originally, by adding some AB to the mix, I added another 4, I'm up to 8. Which means if I used to have, say, a 10% chance, or let's say a 25% chance of AB splitting up to become A and B separately, so I'd have maybe a 25% chance, I would get one of them doing it every second. Now, because I have twice as many, I'm going to end up with 2 of them splitting up in each second. So what that means is maybe this guy's going to split up, and this guy's going to split up. Now, because the A population and the B population separately haven't been increased, what that means is that while some of the old ABs will still come together, the rate of formation of this won't be able to keep up with the rate of destruction. So there's more of these now. I added them. So the rate of this reaction was increased, while the rate of this reaction was constant. So for a little while, there's more of this, and so it naturally reacts to form these guys. And that happens faster for a little while, but eventually the population of the reactants will build up. So this reaction rate will slow, and this one will increase. And a new equilibrium will be formed. The new equilibrium will rest somewhere in between the two conditions. The condition where A and B and AB were before equilibrium and after it was added. So if I were to try and graph this, I would have A and B and AB existing at equilibrium in the first place. And then at this instant, I would add a bunch of AB, but because the rate of this decomposing would now be faster than those ones synthesizing to form it, it would slowly destroy itself, and these guys would increase until the rates equaled back out again, and we'd be back to equilibrium. Now we can see that this supports Le Chatelier's principle because the equilibrium responded to try and get rid of or to try and resist the change. So I added AB, so the equilibrium responded by trying to use up AB. We can also just imagine this from a K perspective. So let's just say that I had my products and my reactants in equilibrium. So let's just say that this is, I don't know, X over Y. And then I add a bunch more products, so all of a sudden this goes up to 2x. over y. Well, now the ratio is going to be 2 times larger. This would be a Q now, not a K, because it's not at equilibrium. Now the products are going to be twice as big as they should be for the reactants, which means I'm going to need less products. And more reactants. Which means the equilibrium is going to shift to try and lower the new population and increase the old population and get back closer to the equilibrium conditions before the shift was made. Let's look at this one more time, but let's look at this from the perspective of increasing the A or the B population, and then we can talk about the collisions. So let's imagine again we're at equilibrium. We have some A's, we have some B's, and we have some AB's. And you're going to notice I'm going to make this equilibrium the same as the original one. Another way to look at this, if I, for example, were to increase the population of B, Le Chatelier would tell us that in order to resist the change to the system, the reaction should shift to the right, using up some of the new population of B. So this population should go up, and these two populations should go down. Well, let's think about why that might be the case. Let's say I added a whole bunch of new B's in here. I'm going to make the new B's blue. Since one of the limiting factors for A combining with B to form AB is the likelihood of a collision between A and B, by adding more B's, it becomes more likely that one of these collisions will occur. What that means then is that for a short period of time, the rate of the forward reaction will grow, while the rate of the reverse reaction remains constant. This will cause a buildup in AB population, which eventually allows these two reaction rates to equal out again and reach a new equilibrium. But this increased chance of collision means that it's more likely that the reaction will happen this way at first than it is that it'll go like that. And so the forward reaction is favored, as Le Chatelier principle suggested. Again, if I have my population A and my population B and my population AB, and we start at equilibrium, and then at some point in time I increase the population of B. Now there's more B's for A to collide with, and the two things start reacting a little bit faster. This is going to deplete the population of A and B. It will also create new AB's and reach a new equilibrium. The equilibrium will be somewhere in between where the old equilibrium was and the equilibrium we're trying to form, but it will also resist the change. So if I increased B, it will drop the concentration of B away due to the increased likelihood of collisions. So that's how you can change a concentration, and it's what Le Chatelier says will happen, but it's also the real reason why that will happen in a variety of, considering the particles, or looking at the K value, or just looking at the graphs.